How does the extension of an elastic cord depend on the original length? P and Q are two identical elastic cords. The length of Q is twice that of P. Click and drag each of the weights W and hang it from the lower end of each cord. Compare the extensions of the cords. Answer: extension of Q is twice that of P.
So that means the extension of Q is 4 cm, the extension of P is 2 cm. Same cord, but end with the same lot, same width of the lot.
The ratio of the extension to the original length is known as strain.
So this means that the ratio of the extension over the original length, we call that is the strain. Strain is equal to extension over the original length.
Click on the hand to view the definition for strain.
So now strain is the the extension of the cord divided by the original length. So this means that strain is a dimensionless quantity and has no unit.
The length of the section OP of a thin wire is 200.0 centimeters. Increase the longitudinal force stretching the wire in steps of 10 newtons by dragging the loads onto the pan. What is the extension? Calculate the strain.
Okay, so from here, the length of the section O to P is 200 cm or equal to 2 meters. Increase the longitudinal force. This means that we increase the load, increase the force, by 10 Newton, and dragging the load into the pan, what will happen? So that means that we drag it and put it. So we notice that extension is 0.2 cm, where from the calculation, strength 0.2 over the original length is 0.01. And if I increase the load again and increase again, so we notice that the extension keep on increase when the force is added. The strength of the system also increase as well.
Summary. Property of a material to regain its original dimensions after a deforming stress has been removed is known as elasticity.
Elasticity means that there is a properties of an object to returns to its original length or returns to its original shape after the applied force is removed. If the object is able to return to the original shape or original length, we said that the object is within the elastic limit. If the object cannot return to the original length or the original shape, this means that we said that the object is out of the elastic limit.
Stress equals longitudinal force over cross-sectional area.
Stress equal to F over A, where the strain equal to?
Strain equals extension over original length.
Strain is equal to extension over the original length.
Unit for stress is Newton per meter square.
So unit for the stress is equal to the pressure, that is Newton per meter square, but for the strain is dimensionless.
Strain is a dimensionless physical quantity and has no unit. How does the extension of a wire vary with increasing force? Click on the load one at a time to increase the force stretching the wire. Observe that the force extension graph is been traced simultaneously.
Ladies and gentlemen, let's look at the graph. The graph shows that is the extension against the force. Still remember the graph of the extension against the force? that is obeys, that is the whose law is it? That is the Hooke's law. So Hooke's law said that the extension is extension of an elastic material is directly proportional to the applied load, provided all the condition without exceed the elastic limit. But this means that the applied load and the extension still within the elastic limit. So observe that, okay, we click on the load and increase. So keep on increase the load. So what will happen? So we notice that when the load increase, when we increase the load, we increase the force applied on the string, the extension of the string or extension of the cord keep on increase as well. So the extension is directly proportional to the force.
What is the relationship between extension and force? Answer: the extension is directly proportional to the force. The relationship between extension and force is given by Hooke's law.
Okay, so we notice that Hooke's law said that the extension is directly proportional to the applied force, given that the within still the system within the elastic limit. So from here, according to Hooke's law, F is equal to Kx or F equal to Ke. E is the extension of the elastic cord or elastic material. And K will be the constant known as the force constant. Hey, what is meant by the force constant? Force constant actually is the stiffness. Let's say if there is a spring or there is a elastic material, so we said that there is a stiffness of the spring, stiffness of the material. Or in other words, we said that is the strongness of the elastic material. So if the spring, let's say a spring, if the spring is strong, this means that the force constant K or the stiffness of the spring or the strength of the strongness of the spring is equal to K. So from here, the force constant, according to the Hooke's law, F is equal to K E or Kx. K is equal to force over the extension. So force over extension, from here, the what is that? The gradient of the force. The slide is very blurred. Okay, ladies and gentlemen, the slide now is blurred or not? So this means that from here, according to the graph, the gradient of the graph, gradient is equal to the extension over the force, E over F. So this means that as we know that K is equal to F over X or F over E. So we said that the K actually is one of half reverse of the gradient. So this means that from here, if we find out the gradient, 1 over gradient will be equal to the force constant or the strongness of the spring.
Summary: Hooke's law states, within the elastic limit, the extension of a wire is directly proportional to the force. Force F equals K times E, where K is the force constant and E is the extension. Young's modulus: wires of different lengths, cross-sectional areas, and made of different materials would have different values of force constant. All wires of the same material, irrespective of their lengths and cross-sectional areas, have the same Young's modulus. Click the hand to derive an expression for Young's modulus.
So from here, Young's modulus is equal to the stress over strength. So from here, once we get it, we find the stress is equal to force over the cross-sectional area, and the strength is equal to extension over the original length.
What is the relationship between the force constant K of a wire and the Young's modulus E of its material? Drag and drop the appropriate quantities for stress and strain in the given boxes. Click on Young's modulus, force, Hooke's law, and relationship to continue the derivation.
As we know that stress is equal to force over the cross-sectional area, and the strength is equal to extension over the original length. From here, Young modulus is equal to F over A over E over L. This means that stress over strain. So from here, the force, from the formula, the force we arrange again. So F equal to EA over L times with the extension. According to Hooke's law, F is equal to Kx, right? So that means substitute Kx into the formula of F. So at the end, we notice that the K actually is equal to EA over L. That means that it will be the Young modulus times with the cross-sectional area over the original length of the material.
The table shows the values for the Young's modulus for 4 different metals: tungsten, steel, copper, and aluminium. Click and drag to hang each of the loads W from the lower end of each wire.
Okay, here we have 4 different positions. Okay, by using the formula, okay, by using the concept of the Young modulus. Young modulus E is equal to F over A divided by extension over L. So from here, Young modulus, they give us a Young modulus, right, will be equal to F L over E A, right? Okay, so FL over EA. So from here, they give us the Young modulus. And here we notice that we just have the extension difference, right? So this means that Young modulus is inversely proportional to the E. Correct or not? Original length. If original length, all of them are equal, or same original length. That means L are equal. Just the difference will be the extension difference. So the greater the Young modulus will be, the smaller the extension. The smallest extension will be this, right? Okay, so the smallest extension will be the greatest Young modulus. Greatest Young modulus will be this one, right? So this means that this will be the will be the tungsten. Okay, and next, second will be 2.0. Okay, this will be 2.0 steel. Copper will be the third, and the longest extension, the greatest extension, will be the smallest Young's modulus.
Compare the extensions of the wires. Guess the material of each wire. Drag the name of the material from the table and drop it in the appropriate box. Click Answer to check your guess.
So now after we, okay, click Answer. Okay, so this means steel, copper, aluminum, and tungsten. So by using the concept where the extension is inversely proportional to the extension, so we get the answer.
Steel cables of cross-sectional area 2.50 times 10 to the power -4 meters square are used in a suspension bridge. The original length of one of the cables is 5.00 meters and support a load of 3.60 times 10 to the power 5 newtons. What is the stress in the cable and its extension? Click solution.
Okay, so steel cable of the cross-sectional area. This is A. I used to a suspension bridge. The original length is 5 meters and support a load of 3 times 10 the power 5 Newton. So from here, what we have the F. F is equal to 3.6 times 10 the power 5 Newton. And L, original length L is equal to 5 meters with the cross-sectional area is equal to 2.5 times 10 the power -4 meter meter square. Okay, so from here, they said that what is the stress? Stress is equal to F over A. And find out what is the extension. If we wish to find the extension, we use F equal to Kx will do. Okay, by using stress over extension, this means that F is equal to 3.6 times 10 the power 5 over the cross-sectional area will be 2.5 times 10 the power -4 meter square. So we get that what will be the stress. And F equal to Kx. So the F is equal to 3.6 times 10 the power 5 Newton equal to K. Is it any K? Okay. The K, what is this? And its extension. They didn't give us the extension, right? So any Young modulus? Okay. So another one is strength is equal to extension over the original length. Okay. If we find out
Summary. Young's steel cables of cross-sectional area 2.50 times 10 to the power -4 meters square are used in a suspension bridge. The original length of one of the cables is 5.00 meters and support a load of 3.60 times 10 to the power 5 newtons. What is the stress in the cable and its extension? Click solution.
Okay, so from here, in this question, they didn't give us the E, the Young modulus of the cable. So in this question should give us the Young's modulus. Otherwise, we cannot solve it. So from here, okay, after we get that just now, 3.6 times 10 to the power 5 over 2.5 times 10 to the power -4. So we get that the stress will be equal to 1/44 times 10 to the power 9 Newton meter square. The Young modulus is equal to F over A, stress over strength, where we rearrange, we get an extension is equal to FL over AE. You notice or not? The question do not provide us the the Young modulus value. So the Young modulus value should provide to us so that we just can solve it. Okay. Now, as a conclusion.
Summary. Young's modulus equals stress over strain. Unit of Young's modulus is Newton per meter square. Force constant of wire K equals E times A over L, where E is the Young's modulus, A is the cross-sectional area, and L is the original length. Determination of Young's modulus of the material of a wire. The Seals apparatus used to determine the Young's modulus of a wire has several features.
So, we use a scale an apparatus, we call that is the Sears apparatus. So this Sears apparatus have the unit similar to the vernier caliper. So let's look at the how we
Try
use
to
it.
give the reason for each of the features shown. Vernier scale, long thin wire, two identical wires. Then click on each feature to check your answer.
So this is the vernier scale. Okay, so we use it so that the extension can be made sure to a higher degree of accuracy. That means we can make sure until 0.01 cm change. We use long and thin wire so that the extension produced is larger and the extension produced is more obvious. If we use shorter cord or shorter string, this means that the extension produced is very small and it's very difficult for us to make the comparison. We use two identical wire because one of the wire as a control set. Another wire as the as the experiment set. So that means we apply the load, let the string extend, and then we can compare how much of the force will make how much of extension. So by the data provided, we can use it to determine the stress and strength, and then for the okay, next.
Click on the load to increase the longitudinal force on the wire in steps of 5 newtons.
So that means we increase the load. We notice that the extension saw and the length of the string recorded and the extension is determined.
Click Graph to observe the graph of extension against load being plotted.
Extension against load, that means extension against the force. So this means that from the data provided, we get that the extension is directly proportional to the force applied. Means that it obeys the Hooke's law, right?
Click on each step to observe how the Young's modulus of the material of the wire can be deduced from the data obtained in the experiment.
So Young modulus is equal to stress over strength, and it will be equal to F over A over E over L. And we arrange, we get that it will be FL over EA. So at the end, so Young modulus, if extension against the force graph, that means that Young modulus will be equal to 1 over gradient. That will be the K times with L over A.
The table shows the data for two pieces of wires, P and Q. Click and drag loads of the same weight to hang from the lower end of each wire. Observe the extension of each wire. Key in your answers for the corresponding value of extension, stress, strain, and Young's modulus for wire Q. Then click Check to check your answers.
So when we hang the load, we notice that the extension is 42, is equal to 2 cm. So another one from 60 cm to 64 cm. This means that the extension will be equal to 4 cm. So from here, L of P, let's say, is the length. Original length is L. This one is 1.5 L, longer a bit. And the diameter, let's say this is D, and Q, what happened? The diameter is half. That means it is thinner. So this means that extension. How about the extension? So from here, okay, two pieces wire of PQ and click and drag of the same weight to hang from the lower end of the wire. They are using the same material. Okay, so I directly, so this means from here E is 2 cm, right? And the Q, there will be double extension. The extension of Q is double. So from here, the stress is F over A. So this means that once the area becomes smaller, this means that the stress will become higher. So by using the strength, length extension over the original length, so because with 1.5, so this means it will become greater. And at the end, the difference, Young modulus, this one is, let's say the Young modulus for P is E. At the end, Q will be 3 times of the original Young's modulus.
Summary. Searle's apparatus is used in the experimental determination of Young's modulus of the material of a wire. Young's modulus equals 1 over gradient of extension force graph times L over A.
Ladies and gentlemen, as the conclusion for today's lesson, property of material to regain its original dimension after a deforming stress has been removed is known as elasticity. Stress is equal to longitudinal force over cross-sectional area, and the strength is equal to extension over the original length. The unit for stress is equal to Newton per meter square, and strength is a dimensionless physical quantity and has no unit. Hooke's law states that within the elastic limit, the extension of the wire is directly proportional to the force, where the force is equal to KE. K is the force constant and E will be the extension. Young modulus is equal to stress over strength, and the unit for the Young's modulus is Newton per meter square. So from here, the force constant of wire K is equal to EA over L, where the E will be the Young's modulus, A is the cross-sectional area, and the L will be the original length of the material. Searle's apparatus is used in the experimenter to determine the deformation of Young's modulus of the material of a thin wire. The condition we use thin wire, long wire, okay, and Young's modulus is equal to 1 over gradient of extension graph. Extension against the force graph times with the L, original length, over the cross-sectional area of the string. Okay, so ladies and gentlemen, that's all for today's lesson. And later, okay, I will post the worksheet in our Telegram group. So I want you all solve the question from now until the end of the lesson. There's 10 a.m. Okay, so that's all for today's lesson. Thank you very much.